let's look at this specific problem. The problem reads that we have 1 gram of octane, a specific mass, that is poured in a calorimeter that contains a very specific amount of water, in this case 1200 grams. The temperature goes from 25 to 33.2. We're also given the heat capacity of the calorimeter, 837 joules per Celsius, and we need to calculate the energy of the combustion reaction for this 1 gram of octane. So one thing that you have to be very aware of in these kind of problems is that for this example, we're given a specific amount of water. That is our clue to know two things. The first thing is that the heat capacity of the calorimeter that we are given in the problem, it's only the heat capacity of the bomb device. Not the bomb plus the water, but just the bomb. Because we have a specific amount of water, and then the second part of that is that, and now we have to calculate the heat that the water is taking plus the heat that the bomb is taking separately. And then we have to put them together in order to get the total heat that was evolved by the reaction. The second part of the problem is that we have to calculate 2 moles of octane. How do we go about solving this problem? Then first thing first, balance a chemical reaction, make sure that you have all the right stoichiometric coefficients and you have the states of each of the components. And remember, again, I'm repeating this again over and over again so it's very clear. The calorimeter setup, it's made out of the bomb plus the water. In this particular example, because we are given a specific amount of water, then we know that we have to calculate these two separately. So let's do that. First, calculate the energy gained by the water. That is always transferred from the reaction. It's a combustion reaction. It's an exothermic reaction. The enthalpy of the reaction is going to be negative. That means that the reaction is given off that energy that it's going to be taken in by the water. Some of that energy is going to go into warming up the water. So the equation that we have is Q for water, mass of water, the specific heat capacity of water times delta T. When we substitute all these numbers, we end up having about 41.2 kilojoules of energy. Now that's the first step. The second step is let's calculate how much went into warming up the bomb device. That bomb device is given by the heat capacity of the bomb. Remember, all the parts are not they're always fixed. Every single time we do experiment 1, experiment 2, experiment 3, it's always the same device with the same components, so there's no parts changing. There's not a mass that we're changing here for experiment 1 to experiment 2. It's always consistent, so the heat capacity is not the specific heat capacity, it's just the heat capacity of the bomb times delta T. What you are going to observe in this case, it's also that delta T is exactly the same number for the water and the calorimeter, the bomb device. So you end up having around 6.9 kilojoules. Now, we know this other relationship that the total energy for the calorimeter setup, the calorimeter system, is going to be equal to the heat that was absorbed by the water plus the heat that was absorbed by the bomb. And that in turn is going to be equal to minus the heat of the reaction. So when we add up the water plus the bomb together, we end up having now around 48 kilojoules, and that's equal to minus the heat of the reaction. Working out the signs, we end up having that the Q of the reaction is minus 48.1 kilojoules for each gram of substance, according to the data from this problem. And remember, the sign makes sense because it is a combustion problem. This combustion problem is energy that is given off, so it has to have a negative sign. Then if we express this in terms of moles, we know how to calculate a number of moles, and then we end up having a number that it's now in terms of kilojoules per mole of octane. So if we have another experiment with 2 moles, then the energy is going to be twice as much as we calculated here. If we want 0.5 moles in a different experiment, it's going to be half of the amount that we calculated here, and so on. So for an example, in this case, they ask us to calculate what happens when we burn 2 moles of hexane, then that's going to be equal to the amount per mole times 2, and that ends up being around minus 1.1 10 to the 4 kilojoules. Now, the next problem is for you to practice. One thing that I want you to observe in this case is for these two problems, we are not giving any specific amount of water. So if it's not explicitly said that you have a given amount of water, then you have to assume that the heat capacity it's already including the water plus the bomb. That's already included. And if you work out the numbers comparing with the example that I just solved, you will see that the heat capacity of the calorimeter system, the bomb plus the water, is in the order of 4 to 6 kilojoules per Celsius, which is on the same order of magnitude of the two heat capacities for the calorimeter system, bomb plus water, that you find in these two examples. So just practice and let me know if you have any questions.